In this video, let's learn about the cosmic rays. Normally, I wanted to actually just to cover two additional topics that actually before the end of the semester. That one of them is cosmic rays, which we will learn in this lecture, and then another one is gravitational wave astronomy. And sadly, that actually we ran out of time, so that actually we will only touch upon the one more the subject today, cosmic rays. So what is the cosmic rays? Cosmic ray is the fast moving charged particles in the universe. Okay, so these fast moving charged particles typically I think mostly the protons, and because they are actually moving really fast, they have large kinetic energy. So when they actually enter into the Earth's atmosphere, they collide with other particles in the Earth's atmosphere, causing the fast moving electrons. And then these fast moving electrons collide with the nearby particles, producing additional the electrons. This actually causing the cascading effect of flood of electrons and then other particles. These particles actually eventually they're basically shining in the atmosphere, so that actually it is known as the cosmic ray shower. Okay, so the cosmic rays are actually is a two can be categorized as a two domain. One is actually the original the cosmic rays before it actually enter into the Earth's atmosphere. Those are the primary the cosmic rays, and the one that actually they manifested as the shower inside of the Earth's atmosphere called the secondary the cosmic rays. Okay? Cosmic rays are actually mostly protons, and 10% of them are, roughly about 10% of them are the helium nuclei. So that helium has the two electrons, but actually the two electrons are actually just lost, so ionized, doubly ionized helium. And about 1% heavier nuclei and 1% electrons and then a positron. This composition actually makes sense when you actually think about the cosmic abundance. So in the universe, hydrogen initially, soon after the Big Bang, was about 92%. Now they're actually and then also 8% of them are actually helium. But gradually over the 15 billion years, the stars actually recycle these materials and then producing more and more heavier the element. So they're actually they're seeing that actually roughly 10% of the helium nuclei and then 85% of the protons and then few others in the heavier the nuclei. That makes sense, that considering the cosmic the abundance, right? And then one interesting fact is actually that there are many more the cosmic ray particles with the lower energy. So let's think about the distribution of the cosmic rays as a function of its energy. These cosmic ray energies are actually mostly the kinetic energy, how fast they are actually traveling. So the really high end of the cosmic rays are relativistic particles. They are actually just traveling through the space at close to the speed of light. Okay? And this, at the beginning, at the low end, still there is 1 giga electron volt is really fast. So 1 giga electron volt is actually even has the energy higher than gamma ray still. The 1 giga electron volt cosmic rays are actually quite prevalent in such a way that actually even at the 1 meter by 1 meter area, that actually that in per second we see that actually about 10,000 the cosmic rays of about giga electron volt the cosmic rays. And I probably have mentioned I think this to you during the lecture of the astronomical detector. So the typical the CCD in the astronomy is about the size of about 2 inches by 2 inches, and this the 2-inch by 2-inch CCD detector observing the night sky, some object, just merely in 1 minute of exposure, I can actually detect tens of thousands cosmic rays. Okay, And these cosmic rays actually in the recorded the digital the frames are actually appearing as a single pixel or maybe 2 pixels, actually just really glowing brightly. Yeah, and the distribution of these cosmic rays as a function of energy, the shown I think plotted is in a log scale, actually has the nice the straight line regions that with the slope of negative point 2.7. So that means actually when it is actually just expressed, that the number of particles is actually inversely proportional to the energy to the minus some exponent. That exponent is actually 2.7. Okay, then at some that actually that energy level around the peta electron volt, that's about 10 to the 15th electron volt, we see some increase the abundance of this the cosmic rays, and that actually the slope that actually they return to the 2.7, then all the way to the really highest end of the energy domain, we are actually seeing the excess of really high energy the cosmic rays. No, I think the known as the anchor. Okay, compared to this naturally occurring, they're actually fast moving charged particles. Man-made particle accelerator, that actually strongest one they ever is Large Hadron Collider, that can actually only accelerate particle only up to the 7 tera electron volt. That's in the only the first, I think the less than half of this range of the detected cosmic rays. Okay, and then when we actually look at the details of this heavier the nuclei cosmic rays, the composition in more details, we can expect that actually that they should their compositions, I think, should they follow roughly the relative abundance of such the element in the universe known as the cosmic abundance. So these blue bars indicating the cosmic abundance, the relative abundance in the universe, I think lithium, beryllium, boron, carbon, nitrogen, and oxygen, and so on. So the reason that actually lithium, beryllium, and then borons are actually less abundant, although that actually they are the three top 5 lightest element, is the way that actually the nuclear fusion works. So for example, to create this lithium, the element, it needs to actually they combine with the helium nuclei with 1 proton. So instead of that actually that helium the nuclei is actually just fused with the addition of proton, more efficient the process is actually 2 helium nuclei actually fuse, or 3 helium nuclei actually collide. So they're actually just more efficient. The formation mechanism is actually causing the more high the carbon and nitrogen and oxygen, so known as the CNO cycle. So that's that, because that is actually more prepared, and then the direction of the nuclear fission, the lithium, beryllium, and borons are actually less produced in the universe. Yet when we actually just analyze the compositions of the nuclei cosmic ray particles, they actually just about the same abundance as the carbon, nitrogen, and oxygen nuclei. It's because that actually the fast moving protons, okay, moving, that actually the most prevalent cosmic rays, that actually there's the protons or the helium nuclei, they actually collide with the other the heavier the nuclei, which is actually carbon, nitrogen, oxygen, and the neon, like that, and then basically is actually just smash and then break up the nucleus, known as the spallation process. When this spallation is happening, that lithium and beryllium and boron nuclei actually are formed. So these are actually that the lithium, beryllium, and boron cosmic rays are actually as prevalent and as abundant as the CNO and another heavier element, contrary to its cosmic abundance, is due to this interaction of the primary the the cosmic rays with the interstellar mediums. So the cosmic rays actually interacting with other the materials. One example that actually we saw was the spallation, right? Then another example is actually when it is actually just interacting with the neutral atom, it actually just knock off the electrons, actually ionizing the materials. And another example was actually so-called the electron, the ions and ion actually just interaction. So when the ion and an ion actually just close encounter and then just feeling the acceleration each other, it actually produces the energy. And then when the energy is actually produced in the radio, it is called the free transition. When the fast moving particle, the ionized particles actually interacting each other, they radiate at the higher frequency domain, such as X-ray. So when it is actually that the ion-ion interaction actually producing these, the radiation and X-ray, for example, it is known as bremsstrahlung. Okay? Another one is actually synchrotron. So as mentioned, that actually in the radio, the video lecture, the ionized particle interacting with the magnetic field and then just causing the synchrotron radiation and gradually losing the energies. And also there are actually these fast moving particles actually can interact with the photons. Okay, so when the photons actually interacting with the basically scattered by the ionized particles, it is known as completon scattering. This is the inverse procedure. So fast moving particles interacting with the photons, okay, then exchange energies. This is actually known as the inverse completon scattering. And this is especially important for the really the high energy cosmic rays in the universe, because universe is full of very low energy the photons known as cosmic microwave background, right? So because of the Big Bang explosion, okay, and then the universe is ever since they're actually expanding, so they're actually the background, the regions are actually just cool down to the about the 3 Kelvin the temperature. So that actually that's 3 Kelvin the temperature correspondent. The radiation is cosmic microwave background. Cosmic microwave background, the photons are actually very low energy. However, for the really fast moving the cosmic rays like this, okay, so known as the ultra high energy cosmic rays, when these ultra high energy cosmic rays are actually meet with the cosmic microwave the photons, it feels that actually that the photons actually that appear as gamma ray photons, okay, because of the relativistic effect. Not only that, actually that this is the rest the particles that are actually not moving, actually that the cosmic microwave background are actually isotropic, same intensity everywhere. But when it is actually just moving at the relativistic speed, it is actually feeling that actually all this radiation or the field surrounding is actually concentrated into the forward direction. Okay? So this is actually famous. I think the hypothesis that actually yet to be confirmed in a real observational sense, in such a way that actually when you move really fast and then getting close to the speed of light, that your back, the scene that actually behind you actually just coming to the foreground, so you can actually see your back in front. That's an interesting effect. So anyway, I think the concentration of field in the forward direction is actually felt by the really fast moving ultra high energy cosmic ray photons, and these actually interact with the cosmic microwave photons. That means actually that ultra high energy the cosmic rays cannot actually really travel that far, because the universe is full of cosmic microwave background photons. Okay, so that means actually the typical highest the energy the cosmic rays can only travel about 10 megaparsecs. before it actually interacts with the cosmic microwave photons. So that 10 megaparsec is actually not that large. So it is 10 megaparsec is about the size of the local galaxy cluster. Okay? So how do we actually really detect the cosmic rays? In one way, let's just divide into the two or the categories. One is detecting the primary the cosmic ray versus secondary the cosmic rays. To detect the primary the cosmic rays, we need to send the detector outside of the Earth's atmosphere. Okay, that way, that actually we can detect the unaltered cosmic rays. That's good, but actually detecting these the primary the cosmic rays, meaning that actually we need to send the detector out of the space, out into the space. That is actually really expensive. Okay, and especially that actually when someone actually trying to focus on the high energy, the cosmic rays that are rare, that actually we need to build a larger detector. That is actually then the cost is actually growing exponentially. So a lot of cosmic ray, the astronomy is actually done through the ground-based detector. It is actually detecting the secondary the shower, so that actually we can build cheaper, larger, and then detectors actually scattered and then covering the large areas. Yet that actually we need to actually somehow implement, use some sort of deduction algorithm, so that actually that from the detected secondary shower, what that actually primary cosmic ray might have been, right? So that actually there has to be some deduction need to be done. Okay, so the detection is actually the usually that actually the cosmic ray detectors actually larger, the detectors are better, especially that actually when you're actually focusing on the ultra high energy cosmic rays. There are actually the energy greater than 10 to the 18th electron volt. These actually number of such the cosmic rays are actually extremely rare. So the square kilometer the area, we're basically expecting only one such cosmic rays per 100 years. So that means actually to detect those, we need to actually build really, really large detector area. Okay, so really good place to set up those cosmic ray detectors is the the dry desert of the United States, because these around the rocky area or the high altitude desert area are actually about 5,000 feet above. So that actually the atmosphere is actually that less, and the nearest cities are actually several tens of miles away. So light pollution is not a problem. And then it has a really high percentage of clear night with a good visibility. So the good examples are actually that the cosmic ray particle array that actually on the Utah the desert. Okay, so this is the picture of Casamia detector array. There are actually about 1,100 detectors are actually just scattered and then separated by about 15 meters apart. Another one is actually in the New Mexico called Stacy. So Stacy is actually basically detecting the Cherenkov light, which is actually Cherenkov light is electrons from the secondary shower, right? So the secondary cosmic rays that are actually interacting with the materials that are actually just radiating the shining light. So this is actually Cherenkov light. The detection is about 212 steerable that the detector. Okay? So these actually that detectors can be they can detect and then tracing the cosmic rays, and we can actually trying to find and then understanding the origin of these cosmic rays, as shown from our own sun. The solar wind is actually radiating away the stream of ionized particles like protons and helium nuclei through so-called solar wind. Solar wind is actually just a typical, the traveling speed of these ionized particles are few hundred kilometers per second. Although that actually is a really fast at the traveling speed for the human point of view, astronomically this is really low end of the energy. the higher energy, the cosmic rays can be created from the supernova explosion, because we know that actually it can heat up, right? It can accelerate. It can heat up. The exploding gas is hot, so that actually produce the ions, and the expanding the supernova explosion shell can actually accelerate particles. The question is whether it can actually produce that actually observed really high energy cosmic rays or not. And tracing the origin of this the cosmic rays is difficult. It's because that actually that cosmic rays are actually interacting with the magnetic field, and galaxies actually have strong magnetic field. So, for example, this is the map of our Milky Way, the galactic field, and say that actually originally that actually the original the cosmic rays actually approaching to our Milky Way in this direction, then this interaction with the magnetic field in our Milky Way that actually basically just bend these cosmic rays, and eventually that actually reach to our side, the radio, or just got cosmic ray detectors. Then this the incoming direction is altered, so that actually we mistakenly believe that actually it was coming from that direction, not here. So this the bend deflection of the cosmic ray traveling the direction due to the magnetic field in our the Milky Way is a problem. So actually to understand the origin of these energies. But the good thing is actually that really high, ultra high energy, the cosmic rays, they don't react very well with the magnetic field. They basically simply just pass through. But the problem is actually that the ultra high energy, the cosmic rays are actually really extremely rare. So that actually it is difficult to observe, right? The question is actually then whether the supernova, the explosion can produce enough the high energy, the cosmic rays that actually we observed. This is the image of one of the nearby supernova remnant known as supernova 1006. That actually the blue light is actually just tracing the high energy particles, and then red hue is actually heated gas, the X-ray coming from the heated gas. By analyzing these images from the Chandra, the X-ray space telescope images, was shown that actually that particles in the supernova, the remnant, can be accelerated up to maybe 10 to the 15th electron volt, but not enough that actually that can really they accelerate anything above the 10 to the 18th electron volt. So ultra high energy, the cosmic rays that actually has the 10 to the 18th through 10 to the 22nd electron volt energy, these cannot be produced by supernova or the explosion. Then how do we actually know what can actually cause these ultra high energy cosmic rays? It is actually still remained as a mystery. The one that actually the fact that actually observed the fact is these ultra high energy cosmic rays appear to be coming from the random direction and then from all direction, meaning they're isotropic. Their sources, their detected positions are actually isotropically distributed. Right? So this means actually that because that actually the supernova cannot actually produce the ultra high energy cosmic rays, any source within our Milky Way galaxy are likely not strong enough to produce these ultra high energy cosmic rays. So it must be the sources outside of our Milky Way galaxy. Then it can be either the nearby galaxies or faraway galaxy. The nearby galaxies, distribution of the nearby galaxies are not isotropic. They are actually concentrated in the small part of the sky. So meaning that actually that the distribution of the isotropic distribution of detected ultra high energy cosmic rays, meaning that actually they should be coming from the far away galaxies. Then there's a problem because of the GGK effect that actually the fast moving relativistic, the cosmic rays interacting with the cosmic microwave background photons. It has the maximum traveling distance of roughly about 10 megaparsecs. So that means actually 10 megaparsecs is barely larger than the size of the local galaxy cluster. So that means actually that ultra high energy, the cosmic rays cannot really originate and then travel from the far away galaxies. So that actually they can appear as the isotropic in the sky. So this the apparently contradicting the observed data, such as like isotropic distribution of these ultra high energy cosmic rays in the sky versus that maximum distance limit they set by the GGK effect is actually not reconcilable yet. So actually we don't have the working model that actually can explain this actually the contradicting factor simultaneously. So we don't know the actually true origin of this ultra high energy cosmic rays. One possible origin is maybe two galaxies colliding, okay? Or the special group of neutron stars that actually has the unusually strong magnetars. Then these magnetars actually can accelerate because they are actually spinning really fast and then really strong magnetic field. They can accelerate ions actually into the really high energy. So that basically it essentially transferring its rotation energy into the small, the relativistic particles, accelerated particles. The question is whether there are enough magnetars in the universe producing that actually the observed amount of ultra high energy cosmic rays. Another possible source is gamma ray burst. Gamma ray burst is actually the short duration of really the intense gamma ray the radiation. It's the lasting is few seconds at most. So that actually this gamma ray burst is highly concentrated energy of the gamma ray photons, and oftentimes that actually that it is actually the radiating away more energy than typical supernova explosion. So maybe something similar to the gamma ray burst mechanism can produce this ultra high energy cosmic rays, or maybe that every galaxy is believed to be hosting supermassive black holes in their core, in their central part, and these supermassive black holes somehow they're actually just accelerating the larger the particles at the relativistic speed. So in short, that actually that the source, there can be some candidate for the originating source of the ultra high energy cosmic rays, yet that it is not solved. So future of the cosmic ray research is actually we need to understand the origin of the ultra high energy cosmic rays, but they are so extremely rare that even to detect them is challenging. So that actually we need to set up establish a really large the cosmic ray detectors on the ground, and eventually that actually on the space that actually we can directly observe the cosmic rays. So the cosmic ray, the astronomy has the interesting aspect and then promising the contribution to the observational astronomy, but actually it has the one big open questions to date. So this wraps up all the lectures of the Astronomy 3010 in 2020, the academic year. So that thanks for that. Actually, just they keep working hard in this class. Okay, so I wish you that actually have the good the holiday break and wrapping up this unusual this semester in a very difficult situation that actually we have been in the pandemic situation. So I wish you the good luck with your final exams and wish you that actually to stay healthy.